Hey everyone, good morning. We're the Smart Space LLM group. My name is Vedant. I'm from Edison.
My name's Jose. I'm from Union City.
I'm Sathvik and I'm from Hillsborough. And I'm Jonathan and I'm from Union City.
And our advisor is Dr. Jorge Ortiz.
So take the following situation. You're alone in the office at 8 p.m. at night and you trip over a wire, fall, hit your head, and pass out. What would you do?
Well, clearly you can't call the cops. Clearly you can't call the ambulance. But what if your environment could? What if your environment could sense that you fell? What if the environment could reach out to the authorities and get the medical assistance you need? Scenarios like these are what inspired us to take a Raspberry Pi computer, as you can see over here, attach this Maestro sensor suite on top of the headers, just like this. And using this Maestro setup, we can collect data about the physical environment. And using this data that we collect from the physical space, we can sort of feed it to a large language model, sort of like ChatGPT, and get physical intelligence about the space around us. And the entire gist of the project is to integrate an LLM into the physical space to, create an intelligent, world around us. And this project specifically focused on creating a robust data collection infrastructure. So how does it actually work? So what you see are these maestros, and we have about 30 or so set up around the orbit office space over there. And what they do is they have about 10 different sensors on them that collect a bunch of data, everything from temperature to humidity to anything in between. And they stream all that data to the server. And that server sits in our professor's office. And the server essentially stores the data, and we run an ML algorithm called YOLO V7 to process all this data. And using the client, which is like your own device, it could be a laptop, a PC, or iPad, or anything, we can sort of access this data. And yeah.
Yeah, so originally we only had 3 working Pis, and now we have around 30. The way that we were able to get these 30 working is through imaging. So for those of you who don't know, imaging is pretty much just downloading an OS or a custom OS onto anything else. So in our case, we pretty much just imaged the SD card from one of the working Pis and did that to the other 30. We did this using Balena Etcher. The download for the imaging process took around 15 minutes, and the actual imaging or flashing took around 2 minutes. So this was the most effective way of being able to transfer all the working files onto the Pis that we have, and that's the way that we're able to now collect sensor data from 30 Pis.
So another way of actually having this set up is by downloading dependencies. And this offers a user-friendly and kind of a tutorial of how to have your own Maestro essentially. And this method requires you to not have a physical micro SD reader, and it also allows you to have greater customization. So you can decide which versions of a package you want, or add only the necessary components and leave all the elements aside. And this whole process was documented on a GitHub we have, which is a code-based platform where all collaborators can input their code to make the project more robust.
Yeah, so one of the features we worked on adding to the Maestros this summer was start and termination control. So previously, we had to either start all of the Pis all at once or end all of them at once. We didn't have any sort of versatility as to which ones we wanted to do. And this led to a lot of time delays. And yeah, it was just very slow and inefficient. So now we added a front end integration with the back end. And essentially, we can on demand start the Maestros and end the experiment. And just to give an overview of what an experiment is. An experiment is basically a set time period where the maestros will be collecting data about the physical environment. And yeah, we got a lot of efficiency gains, and it just made the entire project more versatile.
So we wanted a way of having visual data on the Pi. We tried manipulating the LED lights, but there isn't a real way to actually turn on and off the onboard LED lights of the Raspberry Pi. So we tried blinking it, but overall this like damages the internal hardware of the Pi, which should ultimately be avoided. And this all was documented on the GitHub that we have. And instead, we're going to use a graphical appeal than an actual physical appeal.
All right. So one of the most important things about creating a smart space is to have accurate measurements of the data. So right here, you see our sensor suite, which is the top of the Maestro that has multiple different recording devices for the accelerometer, gas, pressure, air quality, etc. And we wanted to test these to make sure that they work because this is the most essential step in creating an accurate large language model smart space system. And another thing that was really important is that we create a full infrastructure for creating a smart space. And this means that we want to create infrastructure for future developers to be able to add and contribute to the project by increasing the LLM, increasing the infrastructure capability, adding new maestros. And one of the important parts of that was integrating Log Guru, which basically allows us to tabulate outputs and error messages in an organized and human readable way to ensure that developers have the easiest time adding new features and developing the project.
Yeah, so as Vedant mentioned earlier, we added a front-end component to this. So on this front end, we have 8 different easy-to-use features. Our 2 most important being a chart feature that we have that displays the sensor data in real time. And the other important feature is the coordinate grid. It pretty much just shows where the maestros are within the office space. The front-end development was mainly necessary because running experiments in general is very tedious, because in order to do it, you have to have 2 terminals open and set and do a bunch of commands before you can actually run the experiment and collect sensor data. So just having a button would make it a lot easier for anybody else who wants to use any of the sensors.
All right, so probably the most exciting step of our entire project was integrating the machine learning and LLM part of the project. So the most important step here is the ML tagging and identification. So right now we start with raw data. This is the gas and air quality measurements. But to make this interpretable to the LLM, it's important to have a machine learning algorithm that can tag and identify these. So we use YOLO V8, which is a real-time object detection model, to tag objects, recognize humans, and this makes it easier when we feed it through the LLM, which we use the OpenAI API for. And this helps us create a conversational LLM that you can talk with about the weather or how many humans are in the room. And so outside, we have our LLM set up, so please stop by and have a conversation with it. And then the future work. So this is the next steps in taking this project to be more robust and generalizable to other settings to create greater smart spaces everywhere. The first thing is making the test bed completely remote, running on the cloud instead of a physical server. Furthermore, some of our sensor measurements were not as accurate as we wanted to due to the actual physical configuration of the Maestro. And so creating improved sensor measurements will help us develop our LLM and make it more accurate. Furthermore, we had a latency issue and not getting stuff in real time, and we wanted to improve the sampling rate and the frequency.
And then additionally, we also wanted to implement something called weighted average reward models. So traditionally, what these machine learning models do is they try to cheat and find the most optimal route to get the output you'd need. And it sort of corrupts the data in the process. However, using something like a weighted average reward model, it mitigates the reward hacking that these models do and essentially stops it from cheating, ensuring data accuracy, and it makes sure that the predictions are more accurate and more, robust. And yeah, it also provides a more human aligned response. So yeah, implementing this would definitely be another future goal as well. Thank you. And we'd just like to acknowledge Professor Jorge Ortiz, Jenny Shane, and Ivan Seskar, as well as our undergraduate mentors, Matthew, Emma, and Sanchita. Without them, it would not have been possible. Thank you.